Case Western Reserve University's Great Thinkers series proudly presents the Origins Science Scholars Program. These lectures are presented by the Institute for the Science of Origins, a partnership of Case Western Reserve University and the Cleveland Museum of Natural History, with the generous support of Richard Morrison and the assistance of Case Western Reserve University's College of Arts and Sciences, MediaVision, and WVIZ PBS and 90.3 WCPN IdeaStream. Welcome to the Origins Science Scholars Program, a series of talks on current research topics in origins sciences. Hello, my name is Glenn Starkman, Director of the Institute for the Science of Origins, and I am pleased to serve as your host for this series. The talk you're about to watch is entitled The Applications of Quantum Mechanics. As you will soon learn, it was the application of quantum mechanical thinking to describing the electron that led to the prediction and then discovery of the positron, the first example of antimatter. In this talk, Mathur, professor of physics at Case Western Reserve University and a fellow of the Institute for the Science of Origins, will tell you how this prediction and discovery led to the invention of the transistor. These devices make up the integrated circuits that are the brains inside every computer and are the foundation of the digital age. Please enjoy the talk.
So in the last time, we went over the principles of quantum mechanics. So we've done most of the heavy lifting already. This time, we're going to look at some applications of quantum mechanics. We're going to do a conducted tour of some fascinating quantum mechanical phenomena. We begin our tour by going through the looking glass into the strange world of antimatter. A great discovery of the 19th century was that all matter is made of atoms, and that there's roughly 100 kinds of atoms. In the 20th century, in the early 20th century, physicists also realized that atoms are made of electrons, protons, and neutrons, just 3 kinds of particles. In the 19th century, it was a matter of debate whether atoms were real or whether they were just a convenient fiction. But today, we can actually see individual atoms using scanning tunneling microscopy. We can pick them up, we can move them around. And in this image, Eigler and his co-workers at IBM have manipulated iron atoms on the surface of copper, and they've written out a Japanese word for atom. Some of you may have been to the museum this weekend and seen they have a Japanese calligraphy exhibition going on right now. If you haven't, it's a great exhibition, but this seems like a nice culmination to that tradition. In any case, we've come a long way since philosophers and poets first began to write about atoms in antiquity. So let's look at the simplest atom, which is the atom of hydrogen. This atom has just 2 particles in it, an electron and a proton. The proton is much heavier than the electron, although in absolute terms, even a proton is extremely light. But it is much heavier than the electron, so basically it stays put, and we can focus our attention entirely on the motion of the electron. Okay. We learned last time that a quantum system is allowed to have only certain energy states. It's allowed to have only certain allowed energies. And here are the allowed energies for hydrogen. This is the lowest energy that hydrogen can have. And it turns out that there are 2 states in which hydrogen has this energy. That's the next level up. That's the next energy hydrogen is allowed to have. And it turns out that there are 8 states in which hydrogen has this much energy. Okay. Now, of course, the lowest energy state is 1 in which we put the electron either here or there. The next simplest atom is helium. Helium has 2 electrons. That's a little bit complicated. So let me back up and talk about the helium ion. The helium ion, denoted H+, He+, has just 1 electron. Now, in the helium ion, because it's a lot like hydrogen, it has the same kind of energy levels. And the lowest energy state is to put 1 electron over here. In the helium atom, we have the same energy levels, but we have 2 electrons. So what we do is we put 1 electron here and the other electron there. And this brings up a really important principle. You cannot put 2 electrons in the same state. Okay? That's called the exclusion principle. It was discovered by Pauli, who is a great pioneer of quantum physics and who's especially remembered for his sarcasm. One of Pauli's great put-downs for work he didn't like was to say it's not even wrong. But his own great discovery was the exclusion principle. And what the exclusion principle says is that all particles are of one of two kinds. They're either bosons or they're fermions. Fermions have this property that you can't put two fermions into the same state. And electrons, of course, are fermions. Later on in this talk, we will encounter some bosons as well. You can put as many bosons as you like into a given state. And I guess in the pre-talk banter, there was some discussion about perhaps Glenn and Richard are fermions because they don't seem to be over here at the same time. Okay. So to reinforce our understanding of the exclusion principle, let's look at the third simplest atom, which is lithium. Over here, we have 3 electrons. And so what we do is we put the first electron here, the second electron goes there, and then for the third electron, we have no choice but to put it in the next level up. Okay. So that's the lowest energy state of lithium. Now, if we lived in a fictional world in which electrons were bosons, in that world, we could put all 3 electrons into the same state. Okay. And this kind of lithium would have very different chemical properties from ordinary lithium. All of chemistry would be completely different if electrons were bosons. So the fact that electrons are fermions actually plays a very important role in making the world the way it is. Okay, so much for atoms. Now I want to tell you about some extremely important work done by Dirac in the 1920s. So we need to go back to the 1920s. Quantum mechanics, as it existed at that time, what Dirac realized is that quantum physics, as it was known then, was not consistent with Einstein's theory of relativity. And so he set himself the task of unifying quantum mechanics with relativity. And this is a task in which he brilliantly succeeded. He discovered the Dirac equation, which you can see here in this plaque in Westminster Abbey. It's the only equation in Westminster Abbey, I might add. So what did Dirac do? Well, it turns out, fortunately, that all the relativity you need to know is something you've all heard of. And let me explain what this means exactly now in the present context. So we want to go back to classical physics, and we want to look at the energy of a classical particle. It's a free particle, which means there are no forces acting on it. And the question we're asking is, how much energy does it have? According to Newton, the energy of the particle depends on its mass, and it depends on how fast the particle is going. So you can look at the formula, or you can look at the picture. Here I show that the energy of the particle goes up as its speed increases. Okay. Now, according to Einstein, the energy of the particle is given by E is equal to mc squared. What Einstein is saying is that the energy is also proportional to the mass of the particle. But hidden in this formula is the fact that the mass of the particle increases as it moves faster. Okay. And so Einstein's formula produces this result. The energy also goes up with speed. But as you can see, this is quite different from Newton's result. At low speeds, the two formulae actually agree quite well. They just shifted up and down relative to each other. But at high speeds, there's a big discrepancy between the two, a big disagreement between Einstein and Newton. Okay. So it's this formula that Dirac set his eyes upon. Okay. That's the bottom line here. Okay. So the first thing Dirac did was to work with the quantum mechanics of the day and to analyze a free particle, a particle in which there are no forces. You can solve the Schrodinger equation to figure out what energies this free particle might have. And the end result you find is that the energy goes like half mv squared, like Newton's formula. You can display this information in a visual way. You can say that the energy of the particle increases with the speed by making a graph. Another way to visualize this information is to say that it appears that there is no energy quantization. In this case, the energy can have any value whatsoever, so long as it's positive. So I've tried to suggest that by this picture. This picture suggests that the free particle has a continuum of positive energy states. Those are the energies it's allowed to have. Okay? And that's clearly not in agreement with Einstein, because the energy-velocity relationship, according to quantum mechanics, according to the quantum mechanics of the 1920s, is half mv squared. So what did Dirac do? He changed Schrodinger's equation in an appropriate way. He replaced it with the equation, in fact, that we saw in Westminster Abbey some time ago. But we don't need to look at that equation. Let me describe the solutions to that equation. What Dirac found is that there are some states in which the energy of the particle changes with velocity exactly like Einstein predicted. So that's the good news. He found that there were some states in which the energy goes like Einstein's formula. He found that there was a continuum of positive energy states, if you like, states with energy that start here and keep going up. All these energies are allowed for the Dirac particle. So that's the good news. But there's also bad news. And the bad news is that he found that there were also negative energy solutions, solutions in which the energy goes over this range. Okay? And nobody's ever seen a negative energy electron. And so really, it was kind of perplexing at this point whether his equation, what to do with this equation. Many of us might have simply given up, but Dirac was made of sterner stuff. What he decided was, and so this is Dirac's great idea, he decided that the reason we've never seen a negative energy electron is because all the negative energy states are already filled. Okay? In other words, what we think of as empty space is actually a Dirac sea. Empty space is full of negative energy electrons. We never notice them because they're always there. That's what we think of as nothingness. That was Dirac's idea. Sounds pretty crazy, doesn't it? It gets even crazier than that. Because if you believe in this idea, then you should also believe that if you shine light on empty space, once in a while, the light will kick out a negative energy electron and give it energy and make it positive energy. Okay? So Dirac's theory predicts that you can create a positive energy electron out of nothing. And at the same time, you also end up with a hole in the Dirac sea. And so then Dirac asked himself, what kind of beast is this hole in the Dirac sea? What he decided, what he was able to argue, is that this hole also behaves like a particle, which is in many ways just like the electron. It's got the same mass, but it responds to electric and magnetic fields in a different way, in the opposite way. That's what Dirac decided. So in this way, Dirac was led to predict the existence of a new particle, the anti-electron, the hole in the Dirac sea. He predicted that not only are there electrons in the world, but also absences of electrons, which he called the positron, and which behave like particles as well. Okay? What's more, if you pursue this idea further, you would also decide that if an electron met one of its absences, it could fall down and give off energy. So Dirac also predicted that an electron and an anti-electron, an electron and a positron, when they meet, they destroy each other and they give off light. Okay? So these were the predictions of Dirac then, that there are all these particles, and if they meet electrons, they destroy them. Okay? So that does sound seriously crazy. But then let's pick up the story on the other side of the Atlantic. We now pick up, and a couple of years later, we now go over to Carl Anderson, who was a physicist at Caltech, studying cosmic rays using cloud chambers. Cosmic rays are a stream of subatomic particles that come from outer space. There's still a bit of a mystery exactly what they are, but that's a story for another day. The point is that there's a stream of subatomic particles. And the way in which you can observe them is through a cloud, or at least they observed them back then, was using a cloud chamber. Inside of a cloud chamber, you have extremely moist, humid air. And so when a charged particle goes through, when a subatomic particle goes through, it causes the vapor to condense, and it leaves behind a small trail of clouds. And so you can actually see the particle going through. You can see these tracks. Okay? The tracks over there, the ones that are running this way, are tracks of electrons. And Anderson knew these were electrons because they're curving in this direction. He'd applied a magnetic field, and he knew electrons should curve in that, just so in that way. And then there are these mysterious tracks which are curving in exactly the opposite way, but otherwise they look just like electron tracks. Well, those are the positrons that Dirac had predicted. To get this kind of data, Anderson had to go to the top of a mountain because cosmic rays are much more easily observed using balloons or from space or on top of a mountain. And the particular mountain he went on top of was Pikes Peak in Colorado. So this was a great discovery, a sensational discovery, a particle predicted by pure thought, which was then observed a few years later. But now positrons are a matter of routine. They're used to image the body, and in fact, in the hospital across the road, they use them to make positron images. Here I've shown a positron image of the brain for illustration. Okay. So that's Dirac's great discovery. The next target for Dirac was what he had accomplished to this point was to unify quantum physics with special relativity. Special relativity is Einstein's theory of space and time when gravity is weak. Einstein had also figured out what effect gravity has on space and time in what is called his general theory of relativity. So Dirac's next goal was to try and unify general relativity with quantum mechanics. And he tried this problem in the 1950s. And remarkably, he failed this time. And not only Dirac, but everybody else subsequently has failed. This is actually one of the grand unsolved problems in physics today. Okay. So I think this may be a good place to stop for questions and answers. But in the next part of the talk, I would like to return to Dirac's theory and explain how it had this unexpected impact on a technology that's completely changed the world. But for the moment, in summary then, what we've learned is that all particles come in two varieties, bosons and fermions. And fermions have this characteristic. You cannot put two fermions in the same place, in the same state. We've also learned that electrons have antiparticles called positrons. And it's not just electrons. It turns out that every particle of matter that we know about, almost every particle of matter that we know about, is described by Dirac's theory. And every one of those particles also has an antiparticle. And finally, we've learned that this is actually one of the grand unsolved problems, trying to do what Dirac did for special relativity, extend that to general relativity. OK, so this may be a good place to stop and take questions.
What makes the proton basically stay in place?
It's the fact that it's much heavier than the electron. And here maybe I can draw upon a classical analogy. If you think about the solar system, the Earth and the sun are very similar to the electron and the proton. The sun is much bigger. And so in the solar system, the Earth goes around the sun, and the sun barely moves.
What is a positron?
So a positron is like an electron. It's almost identical to an electron, except it's got some properties which are the opposite, the mirror image of the electron. Okay? Its charge is the opposite of the electron. And it's positively charged. That's why it's called the positron. That's a good way to describe it. It's a positively charged electron. But when an electron and a positron meet, they destroy each other.
Is the positron on the outer ring of the atom like the electron?
It could be on the outer ring of some antimatter atom in which you have a positron and an antiproton at the core of the atom. But those things can be made artificially in the laboratory, but they're not found in nature. In fact, you hardly find any positrons in nature, just in cosmic rays. In our vicinity, there don't seem to be many positrons. Sometimes radioactive decay produces them. But really, there are far more electrons around us than there are positrons. And that's actually a deep mystery, why there are so many electrons and so few positrons. Because according to quantum mechanics, the two particles are really similar to each other. They're twins.
The sun is actually in motion. And you said it wasn't, but is the proton actually in motion also?
To some degree, both of them move, yes. The sun also moves a little bit in response to the Earth, and the proton also moves.
Well, the proton is moving through the galaxy at a relatively rapid rate of speed.
That's true.
Is the proton moving at some relative speed?
So I was talking about the relative motion of the two particles. And then, of course, they could have a collective motion where you could throw that atom away, and then both of them would be moving really fast then. But I was focusing on the relative motion.
Okay.
And in terms of relative motion, most of the motion is that of the electron and very little of the proton. And that's true of the solar system as well. The solar system is moving through the galaxy, as you said.
Relative to each other.
Right.
They're not in much motion.
Right.
But the sun is moving at a great rate of speed, and if you will, gravitationally pulling the rest of the solar system with it.
Right.
Is the same thing true for the proton?
Exactly, the same thing is true for the proton, yeah.
Is there any motion that's not relative motion? I mean, don't you have to be able to compare the position of one thing to the position of another thing in order to have motion?
But that's a good point too. So in the discussion we were just having, we were talking about the motion of the sun through the galaxy. That was relative to the galaxy, and you always have to say relative to what. And when I said the sun doesn't move much, and when I said the proton doesn't move much, I meant relative to the solar system or relative to the atom. And to be more precise, relative to the center of the atom or the center of the solar system. And we can refine that statement further also, but yeah.
Give an example of where we might find antimatter.
Yeah, you can, first of all, the cosmic rays seem to contain antimatter. And then there are nuclei, atomic nuclei, which just break up, radioactive nuclei. Some of them give off positrons as well. They just spit off positrons. Sometimes they spit off electrons, but sometimes they will spit off positrons too. So that's another place where you might find anti-electrons. But that's about it, really. And we can make it, of course. We can make it too.
Thank you for joining us. You have been watching Professor Harsh Mathur of Case Western Reserve University discussing the applications of quantum mechanics. For more information on the Origins Science Scholars Program, please visit the Institute's website at www.case.edu/origins. In the first part of his talk, Professor Mathur discussed the prediction and discovery of antimatter. In the second part, we will learn how identical reasoning led to the invention of the transistor, the basic building block of digital electronics. Now we return to the lecture.
Okay, so I'd like to go back. I'd like to stay in this mirror world of Dirac's for just a little bit longer before we move on to the next main topic on our tour. So now I want to move on to the 1930s, where there was a group of physicists studying materials called semiconductors. This was purely scientific curiosity-driven research. They had absolutely no real-world applications at that time. But they did have very interesting quantum mechanics. So there was this guy, Wilson, who's hardly a household name, although his work has, well, transformed the world, really. He was analyzing the quantum mechanics of an electron moving through a silicon crystal. In a silicon crystal, you have silicon nuclei, and they sit at regular locations, shown here in this picture. And so they form kind of the skeleton of the crystal. And then the electrons move through the crystal in a quantum mechanical way. And what Wilson found when he solved the quantum mechanical equation is that the electrons could have energies only in certain bands. They could have energies in this range, or in that range, or in that range. Those were the allowed energy bands. They could not have energies in between the bands. Those were called the band gaps. Okay? And so in silicon, it turns out you have just the right number of electrons to fill up these bands, and you have no electrons left over to fill up those bands. So half the bands are filled, and the other bands are left empty in silicon. Okay. Now, what Wilson did is he applied Dirac's idea to this situation. And he realized that this is a little bit like the Dirac sea. So if you shine light on silicon, he realized that you could create a hole in this band. You could take an electron in this band and promote it to that band. And when you do that, what you'll end up with is an electron up here and a hole down there. And then, by Dirac's reasoning, this hole should behave like a particle too, like a positively charged particle. So the same physics recurs in a material now. And that was amusing, that was interesting to the people who were interested in semiconductors back then. Not many people really, just a few quantum physicists. In fact, you could play an even more amusing game with silicon that you can't do with the universe. And that is that you could dope silicon. And in that way, you could create holes without shining any light. Let me explain what that means. Doping silicon means to add impurities to it. So if you dope it with phosphorus, that you replace some silicon atoms with phosphorus atoms, it turns out that phosphorus has more electrons than silicon. So you have a few extra electrons, and they end up going into this band, which is empty in silicon. This is called N-type silicon, and they learned how to make it in the 1930s. You can also dope silicon with boron. You can replace some silicon atoms with boron atoms. Now, boron has fewer electrons than silicon, and so you don't have enough electrons to fill this band. You get a partially empty band. So this band is full of holes, and this is called hole-doped silicon, or P-type silicon. And again, they learned how to make this in the 1930s. But the point at which all of this moved from being amusing quantum physics to being really important is when researchers at Bell Labs in the 1940s made this sandwich, which looks a little bit like the NPR logo, but what it actually shows is 3 layers of semiconductor. This is P-type silicon. It's got boron. It doesn't have quite enough electrons. It's got holes in it. And then that's N-type silicon, which has phosphorus, too many electrons. And then this is P-type again. You make a sandwich like this, and it turns out that it makes an extremely useful device called a transistor. Okay? And this is the famous Bell Labs transistor from 1947, or rather, it's a replica of it. It's this great big black thing. Of course, they thought it was amazingly tiny back then, but it's this great big thing over here. That's the Bell Labs transistor. And this event is regarded as the birth of modern electronics. Every electronic device in this room, your phones, the computer, everything here, really traces its ancestry back to this transistor, to this Bell Labs transistor. One of the key players in this research, one of the key developers of the transistor is John Bardeen, who has the unique distinction of being the only person to win the Nobel Prize in physics twice. He's one of 3 people to win 2 Nobel Prizes in total. His other prize was for something we will also talk about later in this lecture. But this first prize was for developing the transistor. And here's a descendant of the original Bell Labs transistor. This is a modern integrated chip. This has millions of transistors on an area that's too small to show you. It's like a square millimeter will have 1 million transistors. Okay? And this is really what powers your phone and powers the computer. Well, not powers in the sense of energy, but makes them work, makes them possible. Okay? So it's really quite extraordinary how this very abstract idea of antimatter has now translated into technology. But that said, it's time for the next stop on our tour. So I'm going to move on now and address the question of what is light. And this may be a good place to pause and say something about the relationship between classical physics and quantum physics. Classical physics was a first draft at understanding nature, and quantum physics, if you like, is a second draft. Okay? So quantum physics helps us understand things like the insides of atoms, which classical physics doesn't help us do. But classical physics does have its own domain of applicability. The places where it works really well. And so it would be crazy to not use classical physics to design bridges or cell phone towers or in any everyday life circumstance, really. We can still continue to use classical physics safely. And so in our discussion of light, I'm going to start out by describing light using classical concepts. And only after that will I come and talk about the quantum physics. Okay. So gravity was, of course, the first force that classical physicists understood. But there were many other forces of nature that were known to humans for a long time. For example, in this picture, gravity is obviously not the only force that's acting on this girl's hair. That's static electricity. And then there's the mysterious force that pulls at the needles of compasses and makes them point north. This is magnetism, also known since antiquity. And here, electricity and magnetism combine into a spectacular storm. So in the 19th century, electricity and magnetism were finally understood on the basis of a very radical concept called field theory. And so what I want to do is take a moment to explain what field theory is and why it's such a radical idea. According to field theory, particles have a property called charge. And this charge can be positive or negative. For example, electrons have negative charge, and positrons and protons have positive charge. This classification into positive and negative goes back to Ben Franklin. Okay, but let's stick with the important ideas. So the important idea here is particles have charge. And then the charges produce electric and magnetic fields. For the moment, you should just picture the electric or magnetic field as a kind of halo that surrounds the particle, but we'll try and get a better picture in a moment. So particles have charge, charges produce fields, and then it's the fields that act on the particles. So I have a particle here, it produces a field, and then the field pushes that particle. It's not the particles acting directly on each other. That was the radical idea in the 19th century, because Newton had imagined that all there is to nature is particles, and the particles exert forces on each other. Okay. So how should we picture fields? One of the first people to emphasize or recognize the importance of fields was Faraday, an experimentalist. And here's how he pictured, say, the magnetic field around a magnet. He imagined that there were these lines, field lines as he called them, that emanate from one pole of the magnet and then re-enter in the other pole. Okay? And it's a nice visual way of thinking about it. In fact, many of you may recall having done this experiment in school where you take a magnet and you drop iron filings and then you shake it, and you can pretty much see those field lines that Faraday was talking about. Okay? So that's a nice tangible way to think about fields, but it doesn't actually, but there's a second more abstract way of thinking about fields, which is more powerful. And this second way of thinking about fields was introduced by Maxwell. The way Maxwell would picture this field around a magnet is that at each point in space, he would imagine there's an arrow. The length of this arrow tells you how strong the field is over there. And the direction in which the arrow points tells you which way the field points, because it turns out that fields have directions too. They can point up, down, this way, that way. So the arrow tells you everything you need to know. There's an arrow at every point in space, okay, that you have to picture. It's not actually there, but you have to picture it's there. So this is clearly a very abstract way of thinking about fields. And Maxwell himself found it really abstract and difficult to understand. In fact, he found a convenient way to think about it, which is that he imagined that space was full of a fluid called the ether. And he imagined that electric and magnetic fields were some kind of disturbance in the ether. Okay? That was Maxwell's mental crutch, his way of dealing with having to think about arrows at points in space. But unfortunately, it turns out that there is no ether. And so we do have to think about it in this abstract way, that there are just arrows at every point in space. That's the only way to think about a field. The fact that there's an ether was discovered right here at CASE, and that's another wonderful story, but another story that I can't tell right now. So let's go on with Maxwell and his abstract way of thinking about fields. Not only did he produce this difficult to understand picture of fields, he also discovered the complete laws of electricity and magnetism. And using those laws, he made an amazing prediction. He found that his equations predicted the existence of electromagnetic waves. Okay? Waves, we talked about them the last time. The most visual kind of wave is the wave on the surface of a pond. You throw a stone into a pond and ripples spread out. Okay? That's a wave you can picture. If you were using the ether picture, an electromagnetic wave is easy to understand too. It's just a ripple running through the ether. But unfortunately, we can't think of it in terms of the ether. So the correct way to picture an electromagnetic wave is that this arrow is waving about. Maybe it's just going round and round in a circle, or it's bobbing up and down in some way. In any case, his equations predict the existence of waves. And not only do they predict the existence of waves, but they predict that these waves move at a certain speed, which he can calculate. And when he works it out, he finds the speed is equal to the speed of light. And so he makes the extraordinary connection. He decides that light, which we've all seen which people have seen forever, but nobody knew the nature of it, is in fact an electromagnetic wave. That's Maxwell's great discovery, that light is an electromagnetic wave. But then there's more to this too, because waves are characterized by their frequency. Again, let's think about the water wave. The frequency of the wave is simply the number of times the water goes up and sloshes up and down per second. Okay? That's the frequency of the wave. And you can have waves of all sorts of frequencies, water waves, electromagnetic waves. And so what Maxwell realized is that light that we see actually just represents a very narrow range of possible frequencies of electromagnetic waves. And there must be waves of other frequencies as well. And so he predicted that light has all these related waves as well. Radio and television work down at these low frequencies. We use microwaves to heat food now. Gamma rays accompany cosmic rays. X-rays are used for medical imaging. So there's this whole spectrum of things that people didn't know about that followed from Maxwell's theory. And their observation was indeed what established Maxwell's theory. So this is worth reiterating. This is Maxwell's great legacy, the idea of fields. Okay? So Maxwell's idea is that the universe is composed of particles and fields. According to Newton, we just need to think about particles, but Maxwell says we also need to think about the fields. And he gave one example of a field, which is the electromagnetic field. In particles, when you think about particles, there's the concept of the state of the particle, and we describe the state of the particle by giving its position and velocity. The state of the electromagnetic field is specified by saying what the electric field is and what the magnetic field is everywhere in space. You need to know what both of those are. Okay? That's like position and velocity for electromagnetism. Okay. And then there's Maxwell's equations, which are the laws that govern electricity and magnetism. Okay. Now let's move on to the quantum version, quantum description of light. It turns out in quantum physics, there's an uncertainty principle. Just as you cannot measure the position and velocity of a particle simultaneously, and so you have to completely revise your idea of particle mechanics, so also it turns out you can't measure the electric and magnetic fields simultaneously. And so you have to completely revise your ideas about electricity and magnetism too. Okay. In fact, what this uncertainty principle tells us is that even if you have completely empty space, if you measure the electric field, it won't be zero. Because if it was zero, then there would be no uncertainty, right? So in fact, even if you have completely empty space, when you measure the electric field, you'll get 0 as the answer only on average. Any typical measurement will lead to a non-zero value. And these things are called vacuum fluctuations. They're an inevitable consequence that even empty space has non-zero electric and magnetic fields in it. And this leads to something called the Casimir effect, which was predicted by Casimir in the 1950s. What he realized is that these vacuum fluctuations, if you take two metal plates with nothing between them, just vacuum, the existence of these vacuum fluctuations will pull these plates together. The force is really small. He could calculate it in the 1950s, but now today we have the technology to actually measure these tiny forces. Okay. But the effects that quantum electrodynamics, this quantum mechanical theory of electricity and magnetism, the effects it predicts are not just tiny effects like Casimir, but it also predicts effects that are quite dramatic. It turns out that the electron is like a small magnet, and quantum electrodynamics allows us to calculate how strong a magnet the electron is. And since the 1940s, this has been a great game, a great competition between theoreticians and experimentalists, each side theoreticians trying to calculate it more and more accurately, and experimentalists trying to measure it more and more accurately. And the upshot is that quantum electrodynamics is the most accurately tested theory in all of science. This has been true since about the 1960s. Okay? Here's the current state of the art. This is the most accurately measured value of a certain parameter that tells you how large the electron magnetism is. And this experiment, there's a local angle to this I should mention. The current world record for this measurement is held by a former undergraduate of ours, David Haneke. So that's his experiment. And that's the current best calculation by theory. And as you can see, they agreed to 12 places, and indeed this is the most accurate theory in all of science. The numbers where they don't agree, neither side is actually certain what those numbers are. Okay, so one last point, and then maybe we should take another pause for questions. Another prediction, we saw in the last lecture that electrons, which are particles, we might picture them as billiard balls. In some ways, they behave like waves. It turns out in the same way, light, which classically we think of as a wave, sometimes behaves like a particle. And you can demonstrate this also by doing a double slit experiment. We don't realize that light is made up of particles because any light, the flashlight or the lights in this room, they're so bright, they contain so many photons, so many particles of light, that they just blend into a continuum. So if you send an intense beam like a flashlight through a double slit, you get an interference pattern. It behaves like a classical wave. It hits the screen all at once. And we talked about these patterns the last time. The classical waves, sound, water waves, light, all produce it. But if you make the light very low intensity so that it's coming out one photon at a time, then something very different happens. Each photon goes through the slit, and then it doesn't produce an interference pattern. It just goes and ding, hits the screen over here at one place, and then the next photon comes and it hits over there. And it's in a quite definite place. The ding happens over there. But then once you've sent in thousands of photons, then the interference pattern reemerges, because it turns out that most of the photons land here, very few land there, and then most land here, and then very few land there, and so on. And so this is just like the way electrons produce interference patterns. And so paradoxically, in quantum physics, particles are waves, and waves are particles. In fact, that might be a good summary of this entire section. So perhaps what I will do now is to, again, pause for questions.
What are you actually measuring when you're measuring electricity or magnetism? And how are you measuring it?
OK, that's a great point, because we can actually see the particles, but we can't see the fields. So what we measure is the effect of the fields on the particles. Okay. And so what you always have is a situation where there's one particle that produced the field, and the other, which you can see, and then there's the other particle which experienced the field, and you can see that too. The field that went in between is mostly a theoretical construct. It's just a concept. You can't literally see it. Nonetheless, there is no other way to understand the actions of particles but to assume that these fields really exist. Einstein, so as I mentioned, Maxwell struggled with this concept too of fields because it seemed so abstract and removed from direct experience. Einstein had this way of explaining radio, which also works in the same way, right? Because you have you have an antenna over here you can see, and a receiver over there in Los Angeles, which you can see. And then somehow there's this mysterious electromagnetic field, this radio wave that communicates between the two. We take these things completely for granted, but they puzzled the best minds in the world back at the turn of the century. And so Einstein was asked to explain this once. His explanation was, it's like there's a very long cat, and you pull its tail here, and it meows in Los Angeles. And he said electromagnetism is just like that, except there's no cat.
I didn't quite understand what you meant by your vacuum plates.
By the vacuum plates?
Yes.
Oh, I guess I meant the vacuum. So I meant that they're, let me go back. I should be clearer about this. I think you're asking about the Casimir effect, right? Yes. So what's going on over here is that you have these two plates, and you have absolutely nothing between them. So that's why I'm saying there's a vacuum between them. But according to quantum electrodynamics, even in empty space, there are fields, electric fields and magnetic fields. And what Casimir showed is that these fields act in just such a way that they pull the plates together. Okay? And that's something you would not know if you had not realized that that these quantum effects exist. From gravity, because it's a non-gravity, there is also gravitational attraction between the plates. That's actually smaller, I think. But you have to take both of those things into account and disentangle them.
We hope you've been enjoying the Origin Science Scholars Program with Professor Harsh Mathur. Professor Mathur came to Case Western Reserve University from Yale University by way of Bell Labs, where the transistor was invented. In our final segment, we will learn from Dr. Mathur about quantum mechanical liquids and how they may one day be the engines behind another technological revolution. Now, back to Dr. Mathur.
Okay, so we move on to the final segment, final stop on our tour, where I want to talk about quantum liquids and the theory of nothing. So a good place to start, since we're talking about low temperature physics, is to think about refrigeration. Now, even in prehistoric times, there were a number of techniques people had to cool things down. There was evaporative cooling, which is basically what happens when you leave your cup of coffee lying around. I have a cup of coffee over there, undergoing evaporative cooling right now. But also in prehistoric times, people would gather up ice from the mountains or bring it down from the mountains or store it from winter and store it in deep, dark places and use it all year long. So those were the refrigeration technologies available in ancient times. But by 1748, technology had improved to a point where one could make ice cubes artificially. And then by 1877, it was possible to actually make air liquid. We take that kind of thing for granted now, but again, if you put yourself back in that time, it's astonishing that you can take air, a gas, and turn it into a liquid. You can cool things down that much. The numbers I've written over here are the temperature measured in physics units. I should also have written the temperatures in Fahrenheit degrees, because that's more familiar. Artificial ice cubes, of course, everyone knows that, right? That's 32 Fahrenheit, a temperature that's unfortunately much too common in Cleveland. And then liquid nitrogen, that's about minus 400, which fortunately doesn't, minus 350 Fahrenheit, which doesn't happen even in here. Okay, but then moving on, some of this then began to percolate into technology. Some of this basic science percolated into technology. There was air conditioning by 1900, and frozen food. I'm not sure that's an advance, actually, but it appeared around that time as well. But going back to basic science, the technology had improved to a point where helium, which is, of course, a familiar gas, that's the gas that fills up balloons that float, helium could be made liquid at about minus 450 Kelvin. 450 Fahrenheit, minus 450 Fahrenheit. That's getting pretty close to absolute zero. Absolute zero is the lowest temperature you can have in Kelvin units. That's why physicists like to use these Kelvin units, because they start from zero, the coldest temperature. That's about minus 450 something in Fahrenheit. Okay. And today, the current world record is a billionth of a degree Kelvin. That's as cold as it gets. Ironically now, this temperature is achieved by a variant on evaporative cooling, so we seem to have come full circle. But I don't want to talk about the technology so much as about the strange things that happen when you go to low temperature. Okay? Helium, which is a gas at room temperature, becomes a liquid at 4 Kelvin. And then as you continue cooling it to 2 Kelvin, something very strange happens. It still looks like a liquid, but it's so different now that we consider that to be a different state of matter. We call this a superfluid. It's as different from an ordinary liquid as a solid is or as a gas is. So we really do think of this as a different state of matter. It's a quantum mechanical state of matter. Okay. So what's so strange about a superfluid? Well, one way to characterize any liquid is through its viscosity. If you buy engine oil, you can read the viscosity of it on the engine oil for your car. You can read the viscosity of it on the label. The viscosity measures how sticky the fluid is, how easily it flows. Honey is much more sticky than water, and so it has a higher viscosity. Now, there's two obvious ways to measure viscosity. One is to stick a fluid into a pipe and see how easily it goes through the pipe. That's called the pipe viscometer. And the second way to do it is to take these two cans and to pour the liquid between them, and then to try and turn the outer can and see how hard you have to twist it to make it turn. If you have a sticky liquid, you'll have to work much harder than if you have water. Okay. And these two ways give you the same answer for most liquids, so you can use either one of them. Now let's see what happens when you measure the viscosity of helium. Well, it turns out if you use a pipe viscometer, if you push it through a pipe, then the viscosity gets smaller and smaller, and then at this temperature, 2 Kelvin, where it becomes superfluid, there's no viscosity. It just flows completely, effortlessly. That's why it's called a superfluid. No viscosity at all. Flows completely easily. But stranger than that, if you now measure the viscosity, the stickiness of this liquid, using the torque viscometer, you get a completely different answer. You find that it actually becomes much stickier after it goes superfluid. So which is it? Is it sticky or is it not sticky at all? In the 1920s, people tried to understand this in terms of what they call the two-fluid model. They imagined that it separates into two liquids, one of which is superfluid and the other is sticky. But you can falsify this theory immediately, because if you believe in this theory, when you send helium through the pipe, the sticky stuff should remain behind, and you should be able to collect the superfluid stuff. And then they should measure true. But they don't. The stuff that comes out on this side is just as sticky when you put it into a can. And this stuff over here is just as superfluid if you put it in another pipe. So it's really mysterious. And that's not all. If you forget to cover your container of superfluid helium, it'll just creep over the sides and pour out. Okay? And if you shine light on it, it explodes into a fountain. Now, if you stir an ordinary liquid, you always get whirlpools. Autumn leaves and cigarette smoke curling. It's all very beautiful the way whirlpools form in ordinary liquids. And here's a picture of whirlpools forming in an ordinary liquid, in fact. But if you stir helium, what happens is that at first nothing happens. It won't move at all. But if you stir really hard, then a whirlpool will form. But they're always exactly the same size. So they're called quantized vortices. Quantized vortices. Okay? And if you stir it twice as hard, then two vortices will form. And you can see that in this image from a 1970s paper in Physical Review. They've created the first vortex, and now they've created two vortices, and now they've got three vortices, and so on. And they're all exactly the same size. And they're all created by stirring harder and harder. Okay? So how does all of this happen? Well, all of this is tied to the fact that helium atoms are bosons. Okay? When you go to low temperature, all the atoms go into the same state, because bosons can do that. They're trying to get into the lowest energy state, so they all go into the same state. And that's called Bose condensation. Now, when you have all the particles in exactly the same state, their amplitudes are all perfectly matching, and so that amplifies quantum mechanical behavior. And so you end up with this bucket full of stuff behaving in a quantum mechanical way. And every one of those strange properties I mentioned before can be understood in terms of the quantum mechanical behavior of these helium atoms. So we managed to pull quantum mechanics out of the subatomic realm and make it much more tangible and vivid in this way by going to low temperature. Now, this is amusing, and certainly it will be quite interesting to the half a dozen people in the world who still study liquid helium. But as it happens, this doesn't only apply to liquid helium. This story repeats itself over and over again. It turns out that if you look at metals, metals are full of electrons, and at room temperature, the electrons behave like a liquid. It's this electron liquid that carries currents in the wires that are in the power grid and so on. So metals are full of this electron liquid, and it's an ordinary liquid at room temperature. But when you cool it down at low temperatures, this liquid becomes superfluid. It becomes superconducting. We use a different word, superconductor, because this is a superfluid, but the particles that make it up are also charged. And so that just gives them, well, many more interesting properties. It gives us an extra handle on these particles. Okay. So just like superfluid helium flows effortlessly, so also in a superconducting wire, current flows without any resistance. And so this immediately creates visions of future technology where you might have a power grid in which you can distribute electricity without any energy losses. And such a grid would make our present-day grid look as archaic as this 1890s New York City power grid. The other remarkable thing is that superconductors block electric fields, and they block magnetic fields, and they completely block electromagnetic waves as well. Okay. Let me explain how this works by just looking at how they block magnetic fields. Okay. So if you've got a superconductor, what the magnetic field does is it tries to stir up the electrons. And we learned a little while ago that you can't stir up a superfluid easily. And so the electrons don't get stirred up. And that forces the magnetic field lines to duck around the superconductor instead. They can't pass through the superconductor. You can just see the field lines going around and practically straining and pushing this thing up. And in fact, that's exactly what happens. If you put a superconductor in a magnet, it levitates. Okay, it's floating above because the field lines have to step around it, because this superconductor doesn't like to be stirred. There are many other interesting analogies between superfluids and superconductors, but I think I'm going to pass over these quickly and mention that superconductors already play an important role in technology today. Superconducting magnets play an important role in medical resonance imaging and MRI, and they also have other scientific applications. Also, you can use superconductors to make detectors for medical applications as well as other scientific applications. But on the whole, it's a small market, small niche market. And the reason for that is superconductivity requires low temperature. If someday somebody made a room temperature superconductor, that would completely transform the technology. We could actually then realize all these fantasies of lossless power transmission, of levitating trains, and of all kinds of new electronics. Okay. Now I want to move on from the world of tangible laboratory physics to something more fundamental. I want you to imagine a universe that's filled with a charged superfluid, with a superconductor. What would happen in such a universe? Well, in such a universe, electricity and magnetism, as we know it, would not exist. Remember, superconductors block electric and magnetic forces, so electric forces would become extremely weak in such a universe. And also, light would not propagate in such a universe. It would be a completely dark universe. And clearly, this is not our universe. Okay? So now I want you to think about another imaginary universe. In the second imaginary universe, I want you to imagine that there are two kinds of electromagnetic fields and two kinds of charge. I'll just call them type 1 and type 2. I could call them regular and unleaded. It doesn't really matter. There's two kinds of electric fields and two kinds of charge. Okay? It's just an imaginary universe. And I'm also going to imagine that this universe is full of a charged superfluid, but the superfluid only has type 2 charge. Okay? What's going to happen in this universe? Well, in this universe, the type 2 electromagnetic force is going to be weak, and it's going to be dark as far as the type 2 kinds of electromagnetic waves are concerned, because this superfluid will block those waves. But as far as type 1 electromagnetic force is concerned, that's going to be strong. And type 1 electromagnetic waves, they'll move right through this universe. It's completely transparent. Okay? Now, it turns out that the real world is not so different from this imaginary world at all. It turns out that in nature, there's a force called the weak nuclear force, which is weak, in fact, and that's why it's called that. It also turns out that waves of the weak nuclear force don't propagate through empty space. On the other hand, there's the electromagnetic force, which we're all familiar with, of course, from the playground and compasses and so on. This is a strong force. And of course, electromagnetic waves, most conspicuously light, the universe is transparent to it. So this led particle physicists, sorry, I gave away the punchline. This led particle physicists in the 1960s to speculate that the universe might be full of a superfluid and it's the superfluid that makes the weak force weak. If you drained the swamp, if you completely emptied the universe of the superfluid, then in fact, the weak force would be just as strong as electromagnetism. And so this is the idea, that maybe the universe is full of this charged superfluid called the Higgs field. Now, how would you test this idea that the universe is full of this fluid? I guess, again, because it's always there, we're used to it. We're like fish in very still water. They may not know that they're actually in water because it's always around them. And in the same way, the Higgs field is around us always. This idea, which was just a radical idea in the 1960s, has now become a part of the standard model, which is our best understanding of the laws of physics today. So it's very important to test this idea. And one direct way in which you can test it is as follows. If you have a fluid, you can shake it up. You can send ripples running through it. You can send sound waves running through it. So the most direct test of this idea that the universe is full of Higgs fluid is to create waves in the Higgs fluid. And that's the purpose of this machine, the Large Hadron Collider. Commonly, people say that they're trying to look for, not for the Higgs fluid, but rather for the Higgs boson. But anyone who's survived these lectures knows by now that waves can behave like particles. So waves in the Higgs fluid are the Higgs boson that you may have heard so much about. And as I said, this is the largest machine that was ever built. And one of its primary purposes is, in fact, to shake up empty space. All right, so I think we've come to the end of our tour. And I just want to conclude by pointing to some of the grand problems that lie in our field. And there are many more. It's a really long list. So I just pruned it down to two or three things. One key goal, I think we talked more about this the last time, is that one of the grand challenges is to create quantum effects on a large scale, on a scale that you and I can actually see and experience. Another goal is to create concepts that will help us understand superconductivity in new materials at higher temperature. Many such materials are known. Obviously, there's a practical drive to do this as well, because you might discover a room temperature superconductor. But there's also a fundamental drive to create concepts to understand these materials, because it's in the process of creating these concepts that we understood the Higgs mechanism and the Higgs boson. And finally, of course, the perennial quest to seek a unified explanation of all the forces of nature. Okay. How all of this is going to work out, of course, time will tell. And so maybe I'll let Niels Bohr have the last word. And this may be a good place for me to end.
This lecture is part of the Origins Science Scholars Program of the Institute for the Science of Origins, a partnership of Case Western Reserve University and the Cleveland Museum of Natural History. It has been brought to you with the generous support of Richard Morrison and the assistance of Case Western Reserve University's College of Arts and Sciences, MediaVision, and WVIZ PBS and 90.3 WCPN IdeaStream. For more information on the Origins Science Scholars Program, including a full video archive, please visit the Institute's website at www.case.edu/origins.